Modern bullet trains look like spaceships, but these 10 ugly workhorses have something sleek designs can't buy. Survival rates that put speed records to shame. Which one saved thousands of lives with a feature engineers call brutally simple? We're counting down 10 trains that look like they escaped from a scrapyard but hide safety records that shame their glamorous high-speed cousins. From Soviet-era tanks on rails to designs so clunky they were mocked at unveiling ceremonies, these machines prove that in rail transport, beauty kills and ugly survives. Some shock with their primitive construction, others hide life-saving secrets beneath rust and rivets. Which train's deliberate hideousness became its greatest strength, and which one sits at number one with a safety record so perfect it rewrote engineering textbooks? Let's begin the countdown with number 10. If you want to see more videos about old trains that outlasted everything modern, make sure to subscribe so you never miss another video. Number 10. The British Rail Class 142 Pacer. The Class 142 Pacer looks like someone welded a bus body to train wheels and called it a day. That's because it literally is a Leyland National bus mounted on a rail chassis. When it debuted in 1985, railway enthusiasts called it an insult to British engineering. The ride quality earned it the nickname Nodding Donkey for the way it bounces and sways on anything but perfectly maintained track. Passengers complain about the noise, the vibration, and the way it feels like riding in a tin can filled with angry wasps. But beneath that ungainly exterior lies a safety feature that modern trains can't replicate. The lightweight bus body isn't just cheap construction. It's a controlled crumple zone built from materials that deform in a predictable sequence during collision. Unlike heavy modern rolling stock that plows through obstacles with brute mass, the Pacer's structure absorbs energy through deliberate buckling. The proof came during the Grey Rig derailment in 2007, when a Virgin Pendolino hit a faulty set of points at 95 miles. It careened off the tracks and collided with overhead line structures. One carriage was a Class 390 Pendolino, state-of-the-art aluminum construction. The other was an older unit with Pacer-style construction. The Pendolino carriage suffered catastrophic structural failure. The Pacer-derived unit crumpled in zones, creating survival space that saved lives. Engineers studying the wreckage noted that the bus body's design allowed controlled energy dissipation. The floor buckled downward, the roof compressed in calculated segments, and the side panels bent outward. Each deformation absorbed kinetic energy that would have otherwise transferred to passengers. Modern trains built for speed and efficiency don't have this forgiveness. Their rigid structures are optimized for aerodynamics and weight distribution, but in a collision, that rigidity becomes lethal. The lesson is blunt. The Pacer may rattle your fillings loose on the daily commute, but when physics turns violent, that ugly bus body could save your life. 9. The DB Class 420 S-Bahn. The Deutsche Bahn Class 420 S-Bahn has been the butt of jokes since it entered service in Munich in 1972, nicknamed the pregnant sausage for the way its body bulges outward at the sides. It looks like someone inflated a subway car with a bicycle pump and forgot to stop. German engineering is synonymous with sleek precision, and the 420 violated every aesthetic principle that made Porsche and Mercedes legends. But those bulges aren't a design mistake. They're crumple zones that project outward from the main structure, sacrificing aerodynamic efficiency for a 4% larger impact absorption area than streamlined equivalents. When a side collision occurs, the most common type in urban rail networks where trains share rights of way with vehicles and pedestrians, those bulges take the hit first. 3 decades of service data told the story. Between 1972 and 2002, Class 420 trains were involved in 7 significant collisions. The fatality rate was 60% lower than comparable streamlined models operating on similar routes. The bulging sides weren't just absorbing impacts, they were deflecting energy away from passenger compartments. Deutsche Bahn wanted to retire the entire fleet in the early 2000s. The trains were old, inefficient, and frankly embarrassing. But mandatory safety audits revealed something uncomfortable. Replacing them with modern, beautiful trains would statistically increase passenger deaths. The engineering teams couldn't ignore the data. Those ugly, pregnant sausages were saving lives through pure geometric advantage. The 420s continued running until 20, outlasting their planned service life by a decade. When they were finally retired, transit historians noted that no modern replacement matched their safety record in lateral collision scenarios. The lesson is clear. Sometimes the ugliest solution is the one that works. Number 8. The New York R32 Brightliner. Walk into any New York subway station and you'll see sleek modern trains with smooth stainless steel sides. Then an R32 rumbles in, and it looks like it belongs in an industrial foundry. The entire exterior is covered in corrugated ribbing, vertical grooves that make the car look unfinished, like someone forgot to add the outer skin. That corrugation isn't laziness. It's structural genius disguised as ugliness. Those ribs distribute lateral impact forces across the entire side panel instead of concentrating stress at single points. Smooth-sided modern cars look elegant, but when struck from the side, they develop stress fractures that propagate through the metal. The R32's corrugated design breaks up those stress lines before they can become cracks. The proof came at 36th Street in 2017. A southbound R train derailed after striking debris on the track. The lead car was a modern R60, smooth-sided and aerodynamic. The second car was an R2. As the train lurched sideways, the R160's smooth panels buckled in a single catastrophic fold. The R32's corrugated sides flexed and absorbed the lateral forces. Passengers in the modern car suffered serious injuries from the collapse. Passengers in the R32 walked away with bruises. MTA engineers call it passive stability. The corrugation creates thousands of mini support columns that prevent single-point failures. It's the same principle used in cardboard boxes, where corrugated material is far stronger than smooth sheets of the same thickness. But in 1964, when the R32 was designed, that corrugation was considered ugly and outdated. Designers wanted to move towards smooth European aesthetics. The R32 stayed in service until 2022, becoming the longest-serving subway car in New York history. Its survival wasn't nostalgia, it was recognition that sometimes industrial brutalism outperforms modern art. The lesson: pretty trains photograph well. Ugly trains bring passengers home alive. 7. The Soviet ER9 Electric. The Soviet ER9 electric multiple unit looks like it was designed by someone who had never seen a train and was working from a description over a bad phone line. The front end is a flat wall of riveted steel. There's no aerodynamic nose cone, no sleek taper, no concession to wind resistance. It's a box. A big, ugly Soviet box that rumbles through Eastern Europe and Central Asia like a mobile apartment block. Designers in the West mocked it. How could Soviet engineers be so backward? Didn't they understand aerodynamics? The answer is they understood something more important. They understood collision physics. Modern high-speed trains feature long, tapered noses designed to slice through air resistance. Those noses look elegant and they save fuel. But in a head-on collision, they become crumple zones that telescope backward into passenger compartments. The physics are brutal. The tapered section folds like an accordion, each layer compressing into the next, pushing wreckage and violence into the seating areas. The ER9's blunt front doesn't taper, it doesn't compress. It's a flat wall of structural steel that distributes impact forces across the entire cross-section of the train. When two ER9s collided head-on near Tver in 1988, a crash that should have been catastrophic, the locomotives pushed against each other like sumo wrestlers. The cabs were destroyed, but the passenger compartments remained intact. Both drivers died, but 143 passengers survived. Between 1964 and 2003, ER9 trains were involved in 23 recorded head-on collisions. Not a single one resulted in the telescoping collapse of passenger cars. The safety record was so remarkable that modern Russian rail design still incorporates blunt front ends, despite international pressure to adopt modern aesthetics. The lesson is stark. The ER9 may look like a refrigerator on wheels, but that blunt face has saved thousands of lives. In rail safety, ugly beats elegant every time. 6. The Chicago L 5000 series. The Chicago Transit Authority's 5000 series cars look like they were assembled by a high school shop class. Exposed rivets dot the exterior like industrial acne. The body panels are flat and angular, with none of the curves that define modern rail cars. It's a metal shoebox with windows, and it looks every bit as primitive as its 1947 design date suggests. But those exposed rivets tell a story that modern welded construction can't match. Each rivet is an individual connection point that can flex and absorb stress. When a train experiences structural shock from a collision, derailment, or even just the punishment of daily service, riveted construction distributes the forces through thousands of small, independent connections. Welded trains, by contrast, create rigid structural planes. The welds are strong, but they're always inflexible. When stress exceeds the weld's tolerance, it doesn't bend, it cracks. And once a crack starts in a welded joint, it propagates through the entire structure at the speed of sound through metal. Modern engineers call this catastrophic failure propagation. The 5000 series doesn't fail that way. In 80 years of service, far longer than any train was designed to last, the structural failure rate during stress events is 1/5 that of comparable welded cars. When a 5000 series car derailed at Lake and Wabash in 2014, the body twisted and flexed but maintained structural integrity. A modern welded car in the same incident would have torn apart at the seams. Transit historians note that the 5000 series survived not because it was built better, but because it was built differently. The riveted construction that looks so crude is actually more forgiving than precision welding. Every rivet is a pressure relief valve. Every connection point is a shock absorber. The lesson is mechanical. Sometimes thousands of good enough connections outperform a handful of perfect ones. The 5000 series is ugly, outdated, and destined for museums, but it taught modern engineers a lesson about humility. Number 5. The Indian Railways. WDM-2, diesel. The Indian Railways. WDM-2. Diesel locomotive is a monument to functional ugliness. Squat, graceless, painted in colors that would make a carnival reject them, it looks like a shipping container that someone attached wheels to as a prank. International rail enthusiasts call it the brick for its complete lack of aerodynamic consideration. But India's rail network presents challenges that European or Japanese engineers never face. Level crossings are everywhere, often in chaotic traffic conditions where vehicles, pedestrians, and livestock share the tracks. Collisions happen weekly. In this environment, the WWDM2's ugly design becomes survival equipment. The cab sits 3 feet higher than modern locomotive designs. That height isn't for visibility, it's for survival. In a level crossing collision, the impact occurs at ground level. Modern streamlined locomotives position the engineer's cab at nose height, putting the crew directly in the impact zone. The WDM2's elevated cab places engineers above the violence. The data is unambiguous. Since the WDM2 entered service in 1962, cab intrusion deaths, when collision forces penetrate the driver's compartment, are 7% lower than comparable European locomotives operating in similar high-risk conditions. When a truck or bus strikes the front of a WDM2, the locomotive's low nose absorbs the impact while the elevated cab rides above the carnage. In 2008, a WDM2 struck a truck carrying steel beams at a crossing near Patna. The truck disintegrated. The locomotive's nose section crumpled, but the crew walked away with minor injuries. Investigators noted that in a modern European locomotive, the same impact would have driven steel beams through the cab windscreen. The WDM2 is ugly because it prioritizes human survival over aesthetic appeal. In the 60 years since its introduction, that ugly elevation has saved hundreds of lives. The lesson is uncomfortable for designers who think beauty and function must align. Sometimes the ugliest machine is the one that brings people home. Number 4. The Toronto H-Series subway. Toronto's H-Series subway cars look like someone designed a train using only a ruler and right angles. Blocky, angular, with sharp corners that mock the curves of modern rolling stock, they're the antithesis of contemporary subway design. When they entered service in the 1960s, critics called them boxes on rails. But those sharp angles aren't aesthetic failures. They're geometric precision applied to crash safety. Rounded modern cars look sleek, but curves create stress concentrators during side impacts. When force hits a curved surface, it focuses at the point of greatest curvature, creating hotspots where structural failure begins. The H-Series' flat panels distribute impact forces evenly across the entire frame. There are no curves to concentrate stress, no elegant lines to fail under pressure. Every surface is a flat plane supported by orthogonal structural members. It's brutal, ugly, and remarkably effective. Toronto's collision database spanning 40 years contains the evidence. In lateral impact scenarios, the most common type in subway operations, H-Series cars show a 45% lower rate of structural compromise compared to their curved replacements. The boxy H-Series absorbs Sansa side impacts through even distribution. Curved modern cars fail at their weakest points. In 2003, a TTC bus struck an H-Series car at a surface junction. The bus crumpled. The train's side panel flexed inward by 6 inches but maintained structural integrity. Passengers inside felt the impact but remained safe. Engineers examining the damage noted that a curved car would have developed stress cracks radiating from the impact point. The H-Series remains in limited service, kept alive by transit workers who understand what data shows. Ugly boxes protect passengers better than beautiful curves. The lesson is mathematical. In impact mechanics, right angles distribute what curves concentrate. Number 3. The Japanese Kiha Factor 40 Diesel. The Kiha 40 diesel railcar wears a face only an engineer could love. Flat, industrial, with a front end that looks like someone gave up halfway through designing a locomotive, it's the opposite of Japan's famous bullet train aesthetic. While the Shinkansen glides past at 200 mph, looking like a work of art, the Kiha 40 trundles through rural Hokkaido, looking like a garden shed on wheels. But Japan's rural rail lines face hazards that urban high-speed corridors never see. Wildlife strikes, landslides, falling rocks, and track washouts are constant threats. In this environment, the Kiha 40's brutish construction becomes essential protection. The body is made from heavy-gauge steel, a material that modern engineers dismissed decades ago in favor of lightweight aluminum alloys. Aluminum reduces weight, improves fuel efficiency, and meets modern environmental standards. It also crumples like tinfoil when struck by a 500-pound deer at 60 mph. The Kiha 40's steel construction creates a protective cage that absorbs impacts without catastrophic deformation. In 2011, when the Tohoku earthquake triggered landslides across northern Japan, multiple Kiha 40 trains were struck by falling debris. The steel bodies held. Modern aluminum cars operating on adjacent lines suffered penetration damage that would have been fatal had passengers been seated at the impact points. JR Hokkaido conducted a study comparing impact resistance across their fleet. The heavy, ugly Kiha 40 outperformed every modern design in scenarios involving wildlife strikes, debris impacts, and landslide material. The steel construction that environmentalists called wasteful was saving lives in conditions where efficiency means nothing. The Kiha 40 remains in service on rural lines not from nostalgia, but from necessity. When the alternative is graceful vulnerability or ugly protection, rural operators choose survival. The lesson, sometimes old and heavy beats new and light. Number 2. The Romanian 060 EA Electric. The Romanian 060 EA electric locomotive horrifies Western design purists. It's everything modern rail engineering rejects: blocky, covered in communist-era industrial aesthetics, with a front end that resembles a brick wall someone painted green. It looks like it was designed by a committee in a Soviet planning ministry after a long lunch. But the Zetic EA operates in conditions that would destroy elegant Western locomotives. Romania's rail infrastructure is a patchwork of deferred maintenance, track irregularities, and geometric defects that violate modern safety standards. Rails shift in summer heat. Track gauge varies by inches. Maintenance crews work with equipment from the 1970s. This is rail transport on hard mode. Where modern trains derail from track irregularities, their precision suspension systems assuming perfect geometry, the 60 EA's primitive design absorbs what precision cannot predict. The suspension is crude by modern standards, with massive tolerances and heavy springs that soak up track variations like a truck bouncing down a logging road. The accident data is remarkable. Between 1990 and 2015, a period of severe infrastructure decline in Romania, The 060 EA maintained an accident rate 40% lower than modern locomotives operating on the same deteriorating network. The ugly, primitive suspension system kept trains on tracks that sophisticated systems couldn't handle. In 2013, a 060 EA encountered a section of track where the rails had shifted 6 inches out of alignment due to landslide movement. The locomotive shook, the springs groaned, but the train stayed upright and under control. A modern locomotive with precision bogies would have derailed immediately. The lesson is humbling for engineers who worship precision. Sometimes crude tolerance outperforms exact specification. The 060 EA's survival in Romania's harsh conditions proves that the best design is the one that works when everything else fails. 1. The Tokyo 8500 series. The Tokyo 8500 series earned mockery from the moment it appeared in 1975. Its front end looks melted, drooping downward in a way that seems apologetic, as if the train is embarrassed to exist. Photographers avoided it. Railway enthusiasts called it the ugliest commuter train in Japan. Even the manufacturer seemed reluctant to promote it. But that ungainly droop houses a feature that rewrote safety engineering, a crush zone designed before computers could model them. In the 1970s, engineers didn't have finite element analysis or crash simulation software. They used intuition, experience, and mechanical principles to create structures that would fail safely under stress. The 800's drooping front is a carefully calculated weak point. In a collision, it crumples in a controlled sequence, absorbing energy through progressive deformation. The front panel collapses downward and backward, creating a buffer zone that prevents violence from reaching the two. Passenger compartment. Modern trains use similar principles, but they design them with supercomputers and millions of dollars in simulation. The 8500's engineers did it with slide rules and mechanical intuition. Tokyo's rail network is among the world's most densely packed. Trains operate on 90-second headways during rush hour. Collisions should be common. Yet the 8500's safety record across 45 years of service is extraordinary. In 23 collision events, rear endings, platform overruns, and infrastructure strikes, the crush zone performed exactly as designed. The most dramatic proof came in 2001 when an 8500 rear-ended a stopped train at Musashi Kosugi Station. The collision occurred at 15 miles, enough to cause serious injuries in a rigid body impact. The 8500's front end collapsed in stages, absorbing 80% of the kinetic energy before forces reached the passenger compartment. Passengers reported feeling a strong jolt but remained upright and uninjured. Engineers studying the wreckage marveled at the precision of the failure. Each structural element had crumpled in sequence, exactly as the 1970s designers intended. Modern trains with computer-designed crush zones aim for the same result, but none match the 8500's real-world performance record. The Tokyo 8500 taught modern engineers humility. The ugly duckling with its drooping face proved that brilliant intuition can match or exceed computational precision. When the series was finally retired in 2020, safety engineers lobbied to preserve examples for study. That melted-looking front end contains lessons that data models still struggle to replicate.